this video, we're going to talk about another category of functions called the exponential functions. So the root of the word exponential is exponent. So we're talking about functions that have exponents. Well, we also looked at polynomial functions, and they have exponents. This is going to be a different category of function, and it's based on how the exponent is structured. So the exponents in polynomial functions are different from the exponents in exponential functions. So an exponential function is a function of the form f of x is equal to b to the x power. Okay, so how is this different from something polynomial? Well, if you think about what the polynomial functions looked like, we still have the input x, but it was x then being raised to a power. So something like x squared or x cubed, x to the fourth power, something like that. How is this different? It's different because look at where x is. Instead of x squared, it's now some number raised to the x power. So right now it looks like we actually have two variables. That's not the case. B is currently unknown, but when we look at an actual exponential function, b will be a given fixed number. So b is going to be a fixed number, and then the exponent is our variable. So rather than the exponent being the big number, rather than the variable being the big number, the variable is now in the exponent, so it's moved places. Whenever the variable is in the exponent, we have what we call an exponential function. So x is going to be the variable. X is still our input variable. B is going to be a fixed number, and we have some specific requirements for b. So b has to be a positive number. It has to be greater than 0. If it's less than 0, then we run into some issues with different exponents. So we're not going to consider any situations where b is less than 0. Also, we're going to let b be something other than 1. B could be 1, but if it's 1, nothing happens, because 1 to any power is still 1. So nothing really changes. As we change the x value, nothing happens. So we're specifically going to exclude the case where b is 1. That's going to divide us up into two separate categories for b. So it's greater than 0 and it's not 1. We're going to think of the situations where it's between 0 and 1 as being one particular case, and then the situations where b is greater than 1 as being a separate case. So the constant b, again, it looks like a variable right now, but in an actual function, that'll be a constant fixed number. That's what we call the function's base. So when we're looking at something with an exponent, the exponent is the superscript, and then the big number is the base. It's the number that we're raising to a particular power. And again, in this case, the power is variables. The variable is in the exponent. As we plug in a value to the function, we're plugging it into the exponent. The base is going to stay the same. What's going to change each time we change our input is going to be the exponent. Now, the domain of an exponential is going to be all real numbers. So just like with a polynomial function, we can plug in anything we want to an exponential function and we don't run into any problems. Now, the range, we haven't talked a ton about range, but range is going to be our set of outputs. What sort of y values, what sort of outputs can we get? Well, we can plug in, have any input we want. The domain is all real numbers, but the range is only going to be the set of positive numbers. So when we plug in any exponent, it's always going to give us an output that's going to be greater than 0. So 0 is going to be the cutoff for our graph. So this is an example of what our basic exponential graphs are going to look like. This is actually two graphs on one coordinate plane. So it's not going to look like this each time we graph one. This is two separate graphs on the same coordinate plane. So I want to look at the lighter colored one first, the one that starts below and then increases. This is going to be the shape of the graph when our base is greater than 1. So when our base is greater than 1, then as we increase the exponent, the outputs get bigger. So think of something like a base of 2. Well, if you take 2 and then increase the exponent on a base of 2, the output continues to get bigger and bigger and bigger. So anytime the base is greater than 1, we have a graph that's going to increase, that's going to slope upward over time. And then again, notice it cuts off right there at the x-axis. If we were to continue the graph out further, it's still going to stay above the x-axis. That has to do with the range. The range is always going to be the set of positive numbers, so we can't actually have an output of 0, and we can't have any negative outputs just based on how this function is structured. Now the other graph, that's going to demonstrate the shape of the graph when we have the other kind of base, when our base is between 0 and 1. So think of the base between 0 and 1. Think about like a 1/2 or a 1/3. Why is this graph sloped downward? Well, you have to think about what an exponent would do to something that's fractional, something that's less than 1. Exponents mean repeated multiplication. So if we're squaring something, we're multiplying it by itself 1 time. If we're cubing it, we're multiplying something by itself 2 additional times. If we're multiplying something greater than 1 by itself, then every time we continually do that, we're making the outputs bigger. However, if we multiply something that's less than 1 by itself over and over and over again, the output is getting smaller. If you don't believe that, if that seems strange, try it in the calculator. So say for instance we do 1/3. So I'm going to do 1 divided by 3, there's 1/3. Well, what if we take 1/3 and multiply it by itself? So in parentheses, 1/3 times 1/3. Well, we went from about 0.3 to about 0.1. What if I multiply by another 1/3? So 1/3 times 1/3 times 1/3. In other words, 1/3 cubed. Well, now we're about 0.04. As we continue multiplying, in other words, continue increasing the exponent, this would be 1/3 to the first power, this would be 1/3 squared, this would be 1/3 cubed, so on and so forth. As we continue increasing the exponent, the outputs are going to get smaller and smaller and smaller and smaller. So that's why we're going to have a graph that slopes downward over time. As the inputs, in other words, the exponents, as they get bigger, the outputs are going to get smaller. But the same thing we see with the other graph, we see with this one, just based on how they relate to the x-axis. We're never actually going to get an output that goes to 0. We get really, really, really close, but every output that we can possibly get is always going to be a positive number. Now, some of the key features we see from these graphs. Notice they have this common point. There's a point where they intersect. That point is the point 0, 1. So if we have a graph corresponding to a base greater than 1, or if we have a graph corresponding to a base between 0 and 1, all of those graphs are going to have a point at 0, 1. Why is this the case? What does that mean? Well, this is saying the x value is 0, and when the x value is 0, the y value is 1. I want you to imagine plugging in an x value of 0 to this function. So in other words, our base is a fixed number, we're plugging in an exponent of 0. What happens when you plug in an exponent of 0? Well, let's find out. Now, 0 to the 0 power, what happens when you do that? 0 to the 0 power, there's an issue. We can't actually do that. But we can do anything else to the 0 power. So say we do 1 to the 0 power. Okay, we get 1. What about 2 to the 0 power? Well, that's 1. 3 to the 0 power, 1. Okay, so that looks okay. What about fractions? What about things less than 1? How about that 1/3? What if we take 1/3 and raise it to the 0 power? Well, we get a 1. As it turns out, you're going to get that same output of 1 regardless of what base you choose, unless that base is 0. So regardless of what the base is, if we plug in x equals 0, in other words, we plug in and make the exponent 0, we're always going to get an output of 1 because anything to the 0 power is always going to be 1. So any of these basic exponential graphs is going to cross through the y-axis at 1. So we always have a y-intercept of 1 for the basic exponential graph. Now what about the x-intercept? Well, we don't have any x-intercepts. If the range, if the y values are always positive real numbers, then that means we're always going to be above the x-axis. If we could get a 0 output or a negative output, that means we would have to cross over the x-axis. We don't cross over the x-axis because all the outputs are positive. So there's nowhere where we actually could have an x-intercept. So exponential functions, the basic exponential functions that look like this, are not going to have any x-intercepts. They have that y-intercept at 1, that's consistent for all of them, but they're not going to have an x-intercept. Now, just like our polynomial graphs, these graphs are going to be continuous. They go all the way from left to right, no holes, no breaks, nothing like that. Okay. Now, the x-axis, where we're looking for an intercept but we don't find one, that actually represents an asymptote. So we talked about asymptotes in the context of rational functions. Those were those boundaries. They divided the graph up into pieces. So we had vertical boundaries, stuff to the left, stuff to the right. We had horizontal boundaries, stuff above, stuff below. The x-axis in this case is a horizontal boundary. Everything stays above the x-axis and our graph never drops below it. So as we continue further and further out along both of these categories of graphs, we're going to get closer and closer and closer to an output of 0, to y equals 0, in other words, the x-axis. We get infinitely close, but we're never actually going to touch it or cross it. So that is going to be our horizontal asymptote for these basic functions. Now, I keep saying for the basic functions for a reason. We talked, when we looked at just regular functions, looked at transformations, we talked about the kinds of changes you can make to a function and what those changes will do to the graph of that function. We can apply the same kinds of transformations to a function that looks like this, and they're going to do the same things. So suppose, for instance, we took a function like this and maybe shifted it down or shifted it up, something like that. Well, say we were to shift one of these down. If we shift it down, now it crosses over the x-axis. Essentially what happens is that boundary on the x-axis, it moves with the graph itself. So if we were going to shift the whole graph down 1 unit, not only does the graph move, but any asymptotes the graph has are also going to move as well. So in that situation, we lose that common point there at 0, 1, because the whole graph is shifting, and we also lose that horizontal asymptote there on the x-axis. We still have an asymptote, but it just shifts to a new location. So all of these kinds of things in terms of that common point, the asymptote, that is specific to the basic exponential functions where it's just a base with our basic exponent of x. As soon as we make changes to the function, we add other things on, we make the function more complicated, those kinds of things can change. But they, again, are based on these basic functions that have all of these common characteristics. And again, as we already discussed, if our base is greater than 1, then increasing the exponent increases the outputs. So we're sloped upward left to right as the x values get bigger. In other words, the exponents get bigger, the outputs get bigger. But if our base is between 0 and 1, then as the exponents get bigger, the x values get bigger, the outputs decrease. So we will be sloped downward from left to right. So immediately, as soon as you see any exponential function, you can identify the basic shape just by looking at the base. If the base is something greater than 1, you know the graph is going to be sloped upward from left to right. If the base is between 0 and 1, you know it's going to be sloped downward from left to right. So I want to practice graphing some of these. There's a lot of algebra that goes into exponentials. Some of it we'll be able to explore in the next section we go through. Some of it's a little bit beyond what we're going to be able to do. But exponentials are used a lot in application, so we're going to focus on application more than anything. Now, how do we graph these? So we talked about graphing functions from the standpoint of all of those parent functions. We take a parent function, we identify it from the more complicated function, and then we can apply transformations to it. We can kind of use that principle, but the only issue here is we don't really have parent functions in the sense of a bunch of different graphs that we can just memorize. Why is that? Well, that's because as soon as we change the base, so the base changes, it's a different number, we change the function we're starting with. So x squared is x squared. It never changes. We add on other numbers, it's still the basic x squared graph, just changed a little bit, just variations of it. When we look at exponential functions, changing the number for the base fundamentally changes all of the points on the graph. So we don't really have parent functions here. The easiest way to graph an exponential is just going to be to plot points, which is what we did in the first section when we originally talked about functions. We're just going to focus on plotting points because the points are very specific to every individual exponential with its individual base. So we're going to use the graphing calculator pretty heavily here, specifically that table function that gives us all of those ordered pairs. So let's look at a few. We want to graph each exponential function specifically over the interval from -2 to 2. That means only from the x values from -2 to 2. No negative x values smaller than that, no positive x values bigger than that, using our table of values. Okay, so our first function is going to be f of x is equal to 3 to the x power. Why is this exponential? It falls under this category because the base is a fixed number and the variable is in the exponent. What makes it exponential is where the variable is. If the variable is the big number, if the variable is the base, then 99% of the time we're looking at a polynomial. It's what we call a polynomial function. When they switch places and the variable goes out of the base into the exponent, that's what makes the function exponential. So this is exponential because we can find the variable in the exponent. So let's graph this one. We want to find some ordered pairs in order to get a graph. So how would we do this by hand? Let's do it by hand one time and then I'll show you how you'd use the table. What's really happening here? Well, we're picking some x values and just plotting points. We want the graph from -2 to 2, so we need x values represented from -2 to 2. So easy ones to pick would be -2, -1, 0, 1, and 2. So what are we doing with those numbers? We're substituting them into the function as specific inputs. So in other words, we're evaluating f of -2, f of -1, and so on and so forth. What does that mean for a function like this? Well, it means take that input, for instance, -2, and replace the variable with that number. Here, though, that means we're putting that number into the exponent because that's where our variable is. So if we want to know what the output is that goes with -2, we're going to substitute in a -2 as our exponent. So the base is 3 in this case, and we have an exponent of -2. So up arrow for exponent, and then our exponent is -2. Now be careful when you type this in. Remember, this button is subtraction. This button makes a number negative. So our exponent is -2. And then I hit enter, and that's going to be my output from that. Now this is a number that just keeps going. It doesn't terminate. It just keeps going forever and ever and ever. We're just graphing though, so we're just ballparking it. So about 0.1111 if you want 4 decimal places. More than sufficient. Okay, so that's going to be the ordered pair, -2, and then just a little bit higher than 0. So we go to x equals -2, and then our y value is just a little bit bigger than 0. Now I'm completely aware that goes off the grid and it's hard to graph a number like that, so just do your best. It's going to be between y equals 0 and y equals 1, but it's a lot closer to 0 than it is to 1. So just do your best and ballpark it. Okay, now we want to know what's the output that goes with -1. So we're evaluating f of -1, which means we're plugging in a -1 to our exponent. So 3 raised to the -1 power, 0.33333, so on and so forth. Just round it. why did we end up with decimals here when our base is something that's bigger than 1? Well, it's because the exponents were negative. A negative exponent means something specific. What it actually means from an algebraic standpoint is that you would take the base and you would take its reciprocal. In other words, you'd flip it upside down. So if our base is 3 and we're raising it to the negative 2 power, what that actually means is that we're going to take 3, and the negative tells me take 3 and flip it upside down. So 3, which is 3 over 1, flipped upside down, becomes 1/3. And then you would apply the rest of the exponent, which is the 2. So we would flip the 3 because of the negative, make the 3 a 1/3, take the reciprocal, and then the 2 tells me take the result of that and square it. That's why we end up with something that is going to be less than 1, because essentially the negative is taking this number that's bigger than 1 and it's making it something that's less than 1. And we know repeatedly multiplying by something less than 1, the outputs get smaller and smaller and smaller. So that's why in this case you're going to run into numbers that are smaller than 1 when you have those negative exponents. Now, what happens when we get to 0? Remember, there was that common point on any exponential graph. 3 to the 0 power, or anything to the 0 power, is going to be identically 1. It's always going to be 1. So that is a common point on all of these basic exponential graphs. Now, 3 to the first power, hopefully you can do that without a calculator. It's going to be 3. And then 3 squared is going to be 9. And we only want points from negative 2 to 2, so that's going to give us a nice selection to graph. So negative 2, just a little bit above it for our y value, negative 1, and then about 1/3, so it needs to be higher. Again, obviously we're ballparking it, but it needs to be higher vertically than the previous y value. Now 0, 1, that is in fact on the grid, and then all the other numbers after that are as well. So 1, 3, and then 2, 9. If we were to keep going, what's happening each time? Well, each time we're repeatedly multiplying by a 3. So what you'll notice is that the numbers get really big, really fast. Let's just, for sake of modeling, let's actually do a few more. So what if we did an input of 3, an input of 4, those kind of things. So 3 to the 3rd power would be 27, 3 to the 4th power, 81, 3 to the 5th, 243, 3 to the 6th, 729, 3 to the 7th, 2187. So notice we're only up to an input of x equals 7. That's x equals 7. And we already have an output that's over 2,000. What if we did, for instance, I don't know, 3 to the 20th? Look how big that is. That's 3 places, 3 places, 3 places. So that's 3 billion. That's about 3.5 billion for only an input of 20. What if we did something like 3 to the 100? This is what we call scientific notation. I wanted to see one of these things at some point. You will eventually encounter numbers that look like this. This E, the capital E, what that stands for is times 10 to this power, to this 47th power. What that means is that you would take this particular value, this particular decimal, and you would move the decimal place 47 places to the right in order to get the actual number. Because that number is so large, your calculator can't actually type out the whole number. So it uses scientific notation to abbreviate the number in a more condensed format. Now, what if we did 3 to the 200th? Okay, pretty big. That would be 95 places to the right. What about 3 to the 300? That overflows your calculator. That number is so big that your calculator can't even handle it. Think about that though. That's only an input of 300. Anything bigger than that, it just gets bigger and bigger and bigger and bigger. So you've probably heard people say something is increasing exponentially, it's growing exponentially, and they may or may not have been using that term correctly. But what they mean when they say something like that is that the numbers are getting big really, really, really fast. So exponents, and a fixed exponent like 3, 4, 5, the outputs from those exponents get big fast, but exponential functions, something like 3 to the x, They get big so much faster than polynomial functions that, for instance, by the time we get to an input of 300 for something like this, our calculator can't even handle it. The output is so big. So exponential functions are functions that demonstrate growth at a really, really, really rapid rate. So we can see that from the graph. Look how steeply it's sloped upward. It gets steeper and steeper and steeper and steeper forever and ever and ever. Okay, let's look at another one. These two functions are very closely related. So 3 to the x and 1/3 to the x, very closely related. That's because the bases are reciprocals of one another. So 3 and 1/3 are reciprocals. What we're going to notice is some consistency in the outputs. Now let's do this one using the actual table function. So let's graph this one. So I'm going to clear that out. I want to graph 1/3 to the x power. Now I need to put parentheses around that base. Again, your calculator is very literal. So if you don't put parentheses around that base, it thinks you only mean putting 3 to the x power. So let me type it in the wrong way just to show you what's going to happen. So if we did 1 divided by 3, and then we're raising it, so exponent, and then the exponent is the variable. So we're raising it to the x power. If it does this, if you type this, what it thinks you mean is take 3 and raise it to the x power, and then do 1 divided by all of that. That's not quite what we mean here. What we really want is to take 1/3 as a whole unit and take that whole unit and raise it to the x power. And that is not what we have typed right here. So in order to indicate what we really want, we need to have parentheses around that base of 1/3. So 1/3 in parentheses, and then we're raising it to the x power. That's going to be our exponential function. So let's hit graph. There we go. Give it a moment. Okay, again, yours doesn't look like this potentially. Why is that? Because of the zoom. So I'm going to zoom back to zoom standard, and then you should have something probably close to this. Okay, so notice we have that intercept there at 0, 1. We can verify that from the table. We can also see what's happening with the asymptote. So remember, these graphs, they're going to have an asymptote there along the x-axis. It looks like it's laying on top of the x-axis, actually overlapping with it, but that's not quite the case. It looks like that because we're limited in terms of how accurate our graph can be. But if we were to zoom in and look a little bit closer at what's happening as we go further and further out, then we'll start to see the fact that it's slightly above the x-axis. But again, we're just limited as to how accurately our calculator can graph something like this. But if anything, that gives us the shape that we should expect. So let's go into the table and let's look at some values. So we only want to graph the range from x equals -2 to x equals +2. And I'm way up in the positive numbers from what we did with the last video. Let me scroll back down real quick. And you'll probably find, particularly if you do consecutive videos, you may be in that case as well. So unfortunately, you do have to scroll by hand to get back to the center, back to x equals 0. And that's just the nature of using the graphing calculator. It happens. You just got to have a little patience with it. Okay, there we go. So we want to go from x equals -2 to x equals +2. So at x equals -2, our output is going to be 9. Okay, at x equals -1, our output's going to be 3. At x equals 0, our output is 1. There's that common point. Anytime we plug in an exponent of 0, regardless of the base, the output is going to be 1. And then when x is 1, we're at a third. That's technically what this is. So 1/3 to the first power is 1/3. This is a simplified version of 1/3. It's rounded. And then 1/3 squared is actually 1/9. So if 3 squared gives us 9, then 1/3 squared gives us 1/9. And if you round that as a decimal, 0.1111. Okay, so notice the consistency among these particular y values versus the y values from 3 to the x. It's all the same outputs, but they're in the opposite order. There is a very distinct reason for that. Again, it's because these bases are reciprocals of one another. So when we take 3 and raise it to a negative exponent, we're getting small outputs. When we take 1/3 and raise it to a positive power, we're getting small outputs. So there's some symmetry in these particular outputs, and notice the symmetry occurs around that common point at 0, 1. That's where things flip. So we actually have all the same ordered pairs, but if you imagine taking this graph and flipping it across the y-axis, that will be the graph you'll get for 1/3 to the x power. So anytime you take a particular exponential, graph the exponential with the reciprocal base, you're going to get all the same outputs, but they're going to be in the opposite order. So that's going to be our graph there. Let's look at a couple more. Now I want to take those same exponentials, and I want to look at what happens when we introduce some additional things to the function, specifically the kinds of things that represent transformations. So all of those transformations that we discussed when we talked about elementary functions, just based on the structure, what do we expect for the shape of the graph, what happens when we add something or multiply something, all of those transformations apply no matter what kinds of functions we're looking at. So what happens for this particular function versus another function versus the other one we saw? Well, what is this related to? It's related based on the base. So in this case, the base is 3. So we're comparing it to 3 to the x. Think of this in a sense as the parent function. All of the points we have here, we can think of those as starting points for this particular function. So this function takes 3 to the x power, and then it multiplies that whole thing by a negative. So is this negative 3 to the x, or is it 3 to the x then made negative? It's actually the latter, it's the second. So if we wanted it to be negative 3 to the x, we would have to put parentheses around the negative and the 3. If it's written in this way, what that means is take 3, raise it to this power, and then take the result of that and make it negative. So if you remember when we talked about transformations, taking the parent function and multiplying it by a negative actually represents a reflection. So what that does to the graph is it takes anything above the x-axis, flips it below. It takes anything below the x-axis and flips it above. So if we were to go based on what we know about transformations, essentially what's going to happen is we're going to start with this as the parent function, and then imagine just taking this graph and reflecting it across the x-axis. So all of those points above are going to flip and they're going to go below the x-axis. And so that's going to be the graph we end up with. Now we can confirm that from the graphing calculator. So let's go and let's look at the actual graph for this one. So y equals, okay, I'm going to clear this out. Now, do I need parentheses here? Do I not? In this case, we don't need to put any parentheses because the negative does not go with the 3. It's 3 to the x power, and then we're making the result negative. So I'm going to put a negative, but it's not going to be attached directly to the 3, so I'm not going to put parentheses around it. It's just going to be negative, and then 3 to the x power. Okay, and then let's graph that. And there we go. It's actually the same shape as 3 to the x, but it's reflected. So what if I were to add 3 to the x back in there? So I'm going to add a second graph, and I'm just going to do 3 to the x, the associated graph. There's both of them graphed on the coordinate plane. So here's the actual function that we're graphing. Here's 3 to the x. Notice it's the exact same shape, but the original function has been reflected across the x-axis. And so that's going to be the result. So what's going to happen to all of the outputs? Well, it's going to be the same outputs, but imagine taking the outputs from 3 to the x and then just making them negative. Let's look at that in the table. Now just be aware, if you graph more than one thing, you're going to see 2 columns worth of y values. So which y values you look at are going to depend on which order you graphed them in. So in this case, our first graph corresponds to the actual function we're graphing, so negative 3 to the x. And then the second one, in case the second graph, the second column, is going to correspond to the parent function. But I want to compare the outputs. It's worth looking at them. So we're graphing from negative 2 to 2. So when we're at negative 2, our actual output is negative 0.111. The original output from the parent function is positive 0.111. Same thing with negative 1, negative 0.3 versus positive 0.3. Now when we get to 0, remember we have that point at 0, 1, but here it's saying it's at 0, negative 1. I said it was on every graph. I said 0, 1 is on every graph. Why is it not on this graph? It's not on this graph because this graph reflects a transformation. We reflected from above to below. So that point 0, 1 has been transformed by that negative that's out in front of the function. And then it's going to be the same thing for the remaining two inputs of 1 and 2. We go from the positive version of an input to the negative version of the input, and the graph has just been reflected. Now, as we graph these, I want you to keep in mind all of the different components of the graph. So what's specific to exponential functions? Well, we only graphed from negative 2 to 2, but remember there's an asymptote that goes with these graphs. So this graph has an asymptote on the x-axis. This graph also has an asymptote on the x-axis. This one just happens to approach it on the left, whereas this graph would approach it on the right. As we apply transformations, as we make the exponential functions more complicated, it's important to keep in mind what's happening with those extra features, things like asymptotes. So what would happen with the asymptote for a function like this? Well, if we reflect the graph, we've also reflected the asymptote. Something like that, all the transformations apply to that particular feature as well. Now, the original asymptote for the original graph of 3 to the x was on the x-axis. And then we just took 3 to the x and we reflected it. So if we reflected it across the x-axis and the original asymptote was on the x-axis, what happened when we reflected it? Well, as it turns out, nothing happened when we reflected it. If it's on that axis and we're flipping it across that axis, well, we don't actually see a change. The only change here in terms of the asymptote is how we're approaching the asymptote. So if we look at the original graph, 3 to the x, notice the graph is above it. So we're approaching our asymptote on the left from above, from the positive y values. When we reflect the graph, we're approaching to the left, but now we're approaching from below. That's the result of the reflection. So the asymptote is still there, but the graph is behaving a different way in relation to that asymptote. In this case, we're approaching it from below rather than approaching it from above. Let's look at another one. So f of x is equal to 1/3 to the x, so our other one we graphed, plus 2. So now we have an additional transformation attached to this one. So we're basing it off of 1/3 to the x. Okay, so we can think of this as sort of a starting point for our graph. Now we've taken that particular function and we've added on 2 to that function. What is that going to do? Well, remember, anytime we add or subtract, that represents a shift in the graph. The type of shift is going to depend on where we're adding or subtracting. Is it outside of the function, or is it directly attached to x, to our input? In this case, we're not adding on to x. X is in the input. X is in the exponent. We're adding on to that exponential function as a whole. So it's outside of the parent function. If we're adding on outside of the parent function, then that means we're shifting vertically. Think of it as generating the outputs that come from the exponential function, in other words, getting the y values, and then just adding a 2 to all of those y values. That's essentially what's happening when we're taking that function and we're adding on 2. So this is going to take that original graph and it's going to shift everything up by 2 units. So let's do the same thing with this function that we did with the previous function. So I'm going to clear both of the ones we already have, and then I want to graph both the parent function and the transformed function on the same coordinate plane. So this time let's start with the parent function. So that's going to be 1/3 raised to the x power. Okay, graph that real quick. Okay, remember that's going to be the shape for that one. We already graphed that one. That's the parent function. And then I also want to graph the function with that added 2. Now careful when you type this in. So I've typed the parent function, I want to add on a 2. If I were to just stay in the exponent and add on 2, it's going to put a +2 in the exponent, which is not what's occurring here. The addition of 2 is outside of the exponent. It's outside of the parent function. So in order to execute that, I need to arrow over and then add the 2. That's going to give me the graph that I want. And then let's graph that. So it's already got the parent function. It's going to add on the new function. Okay, so there we go. What happened here? It took the parent function and it shifted it up 2 units. So if we were to compare the outputs, get some actual y values to get an accurate graph, let's go into the table. Second in graph takes us into the table. Okay, we're graphing from -2 to 2. So the original graph at -2 had an output of 9. Our graph has an output of 11. So what happened? We took the original output from the exponential and we added on 2 to that. So we went from y = 9 to y = 11. What about -1? Well, the original function, 1/3 to the -1, we end up getting a 3. We're adding a 2 to that, so our new output is going to be 5. There's that original point at 0, 1. Okay, we're adding on a 2 to the output, so that gives us 0, 3 instead. And we're going to see the same kind of things happen with the actual answers that were decimal. So remember, for an input of 1, we got 1/3. For an input of 2, we got 1/9. Imagine just adding on a 2 to each of those. That's going to give you the new y value. And again, the result visually is that we've shifted the graph up 2 units. So it's a little bit misleading if you look at the graph. It looks like maybe somehow we've stretched it or shrunk it because it looks like they're about to touch each other or cross or something like that. That's not exactly what's going on. It's actually the same shape, but just based on the fact that these graphs start to grow so quickly, it looks like they're really, really close together right there, and they technically are, but they're not growing in the sense that they're going to somehow cross one another at this point. The new graph is not going to cross the old one. It's going to be sloped where it's sort of parallel to it, but it's parallel 2 units above. So just keep that in mind. We didn't actually change the shape. All we did was shift it. We're just seeing one section of the graph. If we could see more of the graph, we'd have a better sense of how one relates to the other. Okay, so we've got our graph. Now let's go back and let's think about the other features, that asymptote. The original graph has an asymptote on the x-axis, okay, at y = 0. Our function took the original graph and shifted it up 2 units. If the graph shifts, everything shifts, which includes the asymptote. So what happened to the asymptote? Well, if it started at y = 0 and we're adding on 2 to all of the function's y values, well then the new asymptote is actually going to be at y = 2. We can see that if we added on to the graph an additional thing. So if I type in y = 2 as an additional graph, you can actually see that new asymptote. So there, my second graph, the one we actually want representing this actual function, it has a horizontal asymptote at 2. So not only did the graph shift, the asymptote shifted as well. So it comes as a unit. The whole unit changes based on whatever transformations we have. Okay, so just to summarize, We can graph using our table with those individual exponential functions. Once we start adding things on, multiplying by a number, adding or subtracting, those kinds of things, we can either use the original functions and just apply those transformations, or we can use the table in the graphing calculator. I would recommend some combination of the two. It's good to start to become intuitive about what something like this negative or this +2 is going to do to the graph. Having that intuitive sense means you're getting to the point where you're really understanding graphing and you're really understanding functions. Okay, let's look at a specific exponential function that is going to be important for some of the applications we're going to do. So it's going to be an exponential function, but it's an exponential function with a specific base that we're going to call e. Now I want to start by just clarifying, we saw an e a moment ago. I think I did like 3 to the 20th, something like that. No, it wasn't that, it was 3 to the 200th, that's what it was. There we go. There was an e right there, okay? This e that we're about to talk about is not the same thing as that e. This e is supplied by your calculator as a way of representing scientific notation. The e we're about to talk about is different from this one. So just be aware, there's two versions. This is a capital E. The e we're going to talk about is a lowercase e. It stands for something specific. So it's a base, it's an exponential base, which means it's a fixed number. The base E stands for Euler number. We pronounce this not Euler, it's Euler. He was a famous mathematician. It's named for him. It's the Euler number, and it's going to be the most common base we see in applications. So in applications where we're modeling something that grows exponentially or decreases exponentially, this is going to be the most common base we see in applications. So E is kind of like pi. It's what we call a universal constant. We all in general know what pi is. It's roughly 3.14. What is pi defined at? Well, it's actually defined as the ratio of a circle's circumference to a diameter. If you take any circle, measure its circumference, measure its diameter, and divide them, the exact number you get is going to be pi. So pi is important in the sense that it pops up a lot and it's universally recognized. So regardless of where you are in the world, if you use the symbol for pi, whether there's a language barrier or not, mathematically we all know we're talking about the same thing when we're talking about pi. E is kind of like that. E is one of those numbers that's just special. It just pops up in the context of real world situations, and it pops up often enough that rather than having to type in the number over and over and over again, they just labeled it kind of like they labeled pi. Now it's relatively straightforward to explain where pi comes from. Where E comes from is a little bit more complicated. It requires some knowledge of calculus to talk about where E comes from. So all you really need to know is, in general, E is about 2.72. Now it's like pi in the sense that it's irrational. So this is an approximation. This is very, very shortly an approximation. An irrational number continues forever and ever and ever and never repeats. Pi does that, E does that as well. So we're actually going to use a button on the calculator for E rather than having to type this in. So you don't need to memorize what E is, you just need to understand what it is, and you need to know how to find it on the calculator. Now, where can you find it on your graphing calculator? First off, if you're curious as to where pi is, so you don't have to type 3.14 ever again, it's on your calculator. So if you find your exponent button, look right above it in blue, there's the symbol for pi. So second up arrow, it types a pi, you press enter, it gives you an approximation for pi. So if you're ever going to take another math class, you want to use pi for something, you never have to type it again, it's right there. Okay. E is actually in two places on your calculator. I'm going to show you both. So if you find where pi is, look right below it at the division button. Right above the division button, between division and the exponent button, you'll see a lowercase e. That is the e we're using. So if you were to do second and divide, it's going to type in e for you. And if you press enter, there we go. So that's the same thing as this, just approximated a little further out. So that's going to be one spot where you can find e. Now that's just the number e by itself. Because e is based on something exponential, in most cases when we use e, we're going to have e with an exponent. So there's also a place where you can find e where it's going to automatically set it up for you to type in an exponent. So if you look on the other side of the calculator, find the LN button. It's actually right next to the 4. It says LN. We'll actually talk about what LN means in the next video. Right above LN, it says e to the x. So the e is the same thing, but what happens when we type this? I'm going to hit second and LN, and it brings up e, but notice what else it does. It also formats it with an automatic exponent. Because again, because this is related to exponential functions, in most cases when we type it, we're automatically going to need to add in an exponent with it. So by using this form of e, it's going to set it up so that you automatically have a spot to type in your exponent. What happens if you use the other one instead? So second and divide. All you'd have to do is press the up arrow, and then it formats an exponent for you. So you can get to it that way if you want, or you can use the one with the exponent already attached. It's not going to matter which way you do it, your choice. So let's type all of this in, and let's actually graph e to the x power. So let's go into y equals. Let's clear out everything we already have. We want to graph this exponential e to the x. And again, you can use e here, you can use e here. I'm going to use the one on the left-hand side because it formats the exponent, and then the exponent is going to be x. Now don't forget, this kind of looks like there's two variables, but e is not a variable. E is a fixed number like pi is. The variable is the x, and the variable is in our exponent. So let's graph that. And there we go. Now just looking at this, it doesn't look much different from 3 to the x in terms of the shape, how it's oriented. It's increasing left to right. It still has that same asymptote. Without zooming in and actually seeing the numbers, you pretty much can't tell the difference. And that's going to be the truth for most exponentials we looked at, particularly because the bases are so close. So 2.7 as a base is really close to 3 as a base, which means 2.7 to the x, 3 to the x, they look pretty much the same. The only way we can differentiate the two is by getting actual concrete values to graph. That's one of the reasons why we use the table. So I'm going to go into the table, and we want to get some values to graph from -2 to 2. Now, I want to start here at 0. You don't actually need the table to know what happens when you plug in 0. E might be a strange number, but e to the 0 power is just like anything to the 0 power. Anything to the 0 power is 1. So e to the 0 power is going to give you an output of 1. So that common point, 0, 1, is also on this graph. It's on every basic exponential graph, regardless of the base. Now, because e is then being approximated by your calculator, just be advised the other outputs you get for any other input are going to be rounded. If the original value for e is irrational, then when we take it and raise it to a power, we still get an irrational number. So keep in mind, all of these other y values you're getting are rounded. But if the goal is just to graph, and graph relatively accurately, just being able to ballpark it with these kind of numbers is going to be enough. So if we were to plug in a -2, we get an output of about 0.14. Plug in a -1, we get about 0.34. We know 0, 1, that's exact. That's not rounded, that's exact. 1 and about 2.72. That's not surprising. Anything to the first power is itself. Well, this is e itself, so e to the first power is itself. And then e squared is going to be about 7.4. So if we were to graph all of these as ordered pairs, just a little bit above the x-axis, just a little bit more, just make sure they go in the correct order in terms of which one's lower, which one's higher. 0, 1, again, that's exact, and then the other two are approximated. Now, if we were to compare this to 3 to the x, 3 to the x gets bigger just a little bit faster. So 0, 1 is common, but once we get past that, 3 to the x is growing just a little bit faster than e to the x is. So when we're at 1 here, we're at about 2.7. When we're at 1 here, we're at 3. When we're at 2 here, we're about 7.4. When we're at 2 here, our output is 9. So this function is going to get bigger faster than this function is. But otherwise, the shape is basically the same. Without seeing those individual concrete values, it would definitely be difficult to differentiate the two. Now, the same kinds of transformations that we see with all the other functions apply here as well. So let's look at a transformed version of the function. We still have e to the x, okay, but now we have two things added in. We've added on a 1 directly to x inside the exponent, and then we've also added on a 3 outside of the function. So we have two transformations here. Now both of them are additions, which means they're both going to be shifts, but they're two different kinds of shifts. So the one outside the function is like the one we just graphed a moment ago. So we took 1/3 to the x, we added on 2 outside, that took everything and it shifted it up 2 units. Well, here we're adding on a 3 on the outside, that's going to shift it up 1, 2, 3 units. What about the +1 that's added on to the x? Well, remember that's going to be horizontal. Anything done to x is horizontal, and it's counterintuitive. Remember, x lies. So if this is shifting us horizontally, if we're adding, intuition says we're moving to the right. It's actually the opposite. If we're adding a 1, we're actually moving it to the left. So this particular function's graph takes the graph of e to the x and it shifts it 1 unit to the left and then 3 units up. And so for one like this, it's definitely going to be useful to graph this in the graphing calculator. So we want 3 plus e to the x plus 1. So I'm going to use the e with the exponent, remember second ln. Now here's where you're going to have to be careful depending on the calculator you have. If you have a newer calculator that actually formats an exponent, you can just type the x plus 1 into the exponent and you're good to go. So I can do that. I'm just going to type in x plus 1 and notice it's all in the exponent. If you have an older calculator that types the e and then does an up arrow, you need to make sure that x plus 1 is inside parentheses inside the exponent. If you don't put it in parentheses after you have that up arrow, then it may interpret it as raise it to the x power and add a 1 onto all of that rather than adding a 1 inside the exponent. So that's going to be another spot where in order to make sure your calculator interprets things the way you want, you're going to need to use parentheses. So just play around with your calculator. Make sure you're getting the same graph that I'm getting for this one, and if you're not, it's probably an issue with parentheses and you want to go back and revisit that. So let's graph this one. There we go. We can definitely see the shift up. The shift to the left is harder to spot, and we're not really going to be able to spot it easily from this one just because the values aren't easy to anticipate. But having a picture, again, is going to give us a sense of what we should expect, and then we can go into the table and we can get some specific values. So at -2, we're at about 3.4. At -1, we're at 4. This is the point that translated from 0, 1. The fact that our y value is an integer and it's not something with a decimal tells us that that came from the other point, the only other point that had an integer output that didn't have a decimal output. So that was where that point shifted. It shifted to -1, 4. And then at 0, we're at about 5.7. Why is it not 0, 1? Well, remember, this is not the original function. This is not a basic exponential. There are some transformations that have been applied. So 0, 1 has moved to -1, 4. Now when we plug in a 0, we're not actually taking e to the 0 power. It's not the same thing. So that's based on the type of transformation we have and the effect that has on our graph. And then at 1, we're at about 10.4. 2, we're about 23.1, which is definitely going to fall off our graph. So again, just ballpark it, do your best, and we should have something roughly like this. So same shape, just shifted to the left, and then shifted up 3 units. So what's happened to the asymptote here? Every basic exponential function has an asymptote on the x-axis. Well, what about the shift to the left? We shifted 1 unit to the left. Does that affect the asymptote? Well, picture where the asymptote is for the original function. If we shift the graph to the left 1 unit, we also shift the asymptote to the left 1 unit. Does that change it? The answer is no. If it's a horizontal line, you shift it left, you shift it right. You may be seeing a different section of the line, but a line is infinite. It continues in both directions. It doesn't look any different from what you saw before. So that shift to the left, the +1 that shifts us to the left, doesn't actually change the asymptote. It's still at y = 0. Now what about the +3? Remember, that's a vertical shift. We shift the graph up 3 units, we shift the asymptote up 3 units. That transformation does change the asymptote. If it's a horizontal line and we're shifting it vertically, it does change the actual asymptote itself. So if we shift the graph 3 units, we shift the asymptote, which takes it from y = 0 to y = 3. So that would be our new asymptote. Let's verify that on the graph. So here's the actual graph. Let's make sure the asymptote is where it should be. So if we graph y = 3 on the same coordinate plane, sure enough, it draws our asymptote and we're approaching it the way we should be. If you draw it anywhere below or anywhere above, it's going to be clearly below the graph or it's going to cross through the graph. So you can verify that it is the asymptote that you want by making sure that your graph essentially lays on top of it, which is what the graph is going to do with any of these horizontal asymptotes. Okay, so we've done a little bit about graphing. We know how to graph in the calculator. Hopefully you have a better sense of what exponential means versus polynomial. So remember, polynomial means we're plugging in inputs to the base, to the big number. Our exponents are fixed values. The base is what's changing as we plug in specific inputs in place of x. When we're looking at something exponential, the base is going to be a fixed number, and when we plug in specific inputs, they get plugged into the exponent. So the base is fixed, the exponent is what changes based on the inputs we're using. So I want to look at a couple of applications for exponential functions. Again, we're going to see these a lot. We're going to see them specifically next chapter when we start talking about financial math. So there's one particular situation where we use this number e in order to calculate some things involving interest. So we'll revisit that when we get there, but suffice it to say, exponential functions pop up a lot. They're very much applicable to real life. So when we talk about something that changes exponentially, typically we talk about it growing or decaying. So growth, of course, means something's getting larger. Decay means something is getting smaller. So if you think about what the basic exponential graphs look like, back to the first page, the basic exponential graphs. The graph where b is greater than 1, our base is greater than 1, that would be the graph that demonstrates the growth of a particular value. So the outputs, we're thinking of what's happening to the outputs. Are they getting bigger? Are they getting smaller? If we're following a graph where b is greater than 1, then as our inputs increase, our outputs also increase. So we're talking about the growth of the output. In this case, when b is greater than 1, the outputs are growing. Now, if b is between 0 and 1, that would be the situation that's described by decay. So as our outputs increase, as our inputs increase, the outputs, the y values, are decreasing. Now, when we look at applications, in a lot of situations, we're only going to focus on the right-hand side of the graph. In other words, where our inputs are positive numbers. In a lot of cases, the input that we think of is representative of maybe time, something like that. So if we think of the input as being 0, thinking of that as starting the stopwatch, in a sense. So when the input is 0, we start counting. If we were to look to the right, then that means time is increasing. It means the stopwatch is running, time is increasing, and we're looking at the resulting outputs from time increasing. If we look to the left of the y-axis, that means time is going backwards. So if this is time is 0, in other words, we start the stopwatch, this section of the graph isn't actually meaningful in the actual context because that would be a portion of the graph where we're talking about negative time. In general, negative time is not meaningful in most situations. So we're typically just going to focus on the right-hand side of this graph. That's going to give us the information we need. So let's look at a situation where something is growing, and then we'll also look at a situation where something is decaying, where it's shrinking. Okay, so our general model is going to be of this form. It's going to be y is equal to c times e to the k times t power. Okay, now there's a lot of variables here, but as with the polynomials where it looks really complicated, when you're looking at an actual problem, it will not all be variable. There will be other things involved and it won't be variable. Okay, so what is actually variable? Well, we know e is not variable. E is a fixed number. Y is variable. Y represents our output. So sometimes we use f of x. We can use y instead. Here we're using y. K and c, right now they look variable, but those will be actual numbers when we're looking at a real problem. Those are constants. Right now they're unknown constants, but in an actual problem, the c will be a coefficient, and then the k will be a coefficient for t, and those will be actual fixed numbers. T is what we're going to think of as our input. So before we've been using x, here we're going to use t to represent time. So in most of our growth and decay applications, we're thinking of our input as time. What's happening over time? Are things getting bigger over time, or are things getting smaller over time? So t is going to be our input. So when we graph, if we wanted to graph something modeled by this function, the vertical axis represents y, and the horizontal axis, what we normally think of as x, is going to represent t for time instead. So that's going to be our input. So again, c and k are going to be constants, and each of these serves a very specific role. So c, our coefficient for the exponential, tells us the original amount of our population when t equals 0. So we're talking about a population. We're talking about an amount to start with. When time is 0, in other words, right at the moment we start the stopwatch, the number for c represents how much we're starting with in our population. We could be starting with nothing. Maybe we're starting with something more than that, and then we're increasing from there, or we're decreasing from there. Now, K is what we call the relative growth rate. That's going to determine how fast our population grows or shrinks. So if K is a positive number, then that means our situation is a situation involving growth. Our base is something bigger than 1. So in general, increasing the exponent makes the outputs bigger. If K is a positive number, then all of our inputs are going to be positive numbers. So e to a positive number that's getting bigger and bigger and bigger, we have outputs that are getting bigger and bigger and bigger. Now, if K is negative, that means our function models decay. It means things are shrinking. So that would be taking our positive base, which is greater than 1, but raising it to a negative exponent. If we raise this base that's greater than 1 to a negative exponent, well, that means we're actually decreasing over time. So knowing what K is going to tell us which of these two situations we're in. So just to reiterate, C is going to be the original amount. It's how much we start with when time starts. And then K tells us, are we increasing if K is positive? Are we decreasing if K is negative? And then the bigger K is, the faster we increase or the faster we decrease. So let's look at a situation where we're growing, and then we'll also look at a situation where we're shrinking, where we're decaying. Okay, so this is a situation involving growth. So cholera, an intestinal disease, is caused by the cholera bacteria that multiplies exponentially. The number of bacteria grows continuously at a relative growth rate of 1.386. In other words, the function that models our population is going to look like this. Now notice we have the variable t. Now we have the variable n. Y has been replaced by n. N is a little bit more descriptive. Think of n as just number. N stands for number. So n is equal to n sub 0, we'll talk about that in just a second, times e to the 1.386 times t. 1.386 is our growth rate, so that's multiplied by t for time, with t being our input. This is going to model how our population of bacteria grows. N is the number of bacteria present after a certain amount of time, which we're going to model in hours. And then n sub 0 is the number of bacteria present at the start. So right now it's a variable, but what else are we about to be told? We've been told that we start with 25 bacteria. So that means from this model, 25 is where we start. So we're going to have a 25 where n sub 0 is. That's going to be the number we start with. So after that, the only variables we have are going to be n, which represents our output, and t, which represents our input. Okay, so based on this model, and based on knowing we start with 25 bacteria, so we have 25 as our coefficient for E, what we want to know is how many bacteria to the nearest unit are we going to have after certain periods of time. So the first length of time is going to be 0.6 hours. So after 0.6 hours have elapsed, how much bacteria do we have in this particular population? So what does it mean? That means this is the value for t, and we want to evaluate this function with t equals 0.6. In other words, we're substituting it in place of the variable t. Now remember, n sub 0 is now 25. That's our starting value, and we've been told that we start with 25 bacteria in the population. So 25 times e to the 1.386 times t, which is 0.6. So what we're doing now is we're evaluating this. We want to simplify this. And of course, you're going to do that in the calculator. You can type that in pretty much as written. So 25, you can type times if you want, or if you immediately go and input the e, your calculator understands that you're intended to multiply right there. So you're good. Now, notice there's a couple things in the exponent. So again, if you have a calculator that formats the exponent automatically, you can just type these in with multiplication between them. If you have a calculator that draws an up arrow, make sure you put parentheses around everything that's in your exponent. So mine formats it, so it's going to be 1.386. Oops, that's not going to do it. That's not a point. Let me clear that real quick. 1.386, I accidentally put a negative, 1.386 times 0.6, and notice that's all in the exponent. So that's what I want. Double check it, read through what you type before you press enter. That looks good. So then I can hit enter. Okay. Now, why did they tell us to round to the nearest unit? Well, when we're talking about something like bacteria, we're talking about something that we can count. We can't have a fraction of bacteria, of a bacterium. That's the singular of bacteria. We can't have half of one. We have whole units. We're counting whole units. So rounding to the nearest unit makes sense in the context of this kind of problem, since we can't have a fraction of this kind of thing. So rounding to the nearest unit, that's going to be 57. So in this case, after 0.6 hours, we have 57 bacteria. So we've grown from 25 to 57. Okay, how about 3.5 hours? So now 3.5 hours, it sat there, it started at 25, how much is in it now? Well, same kind of thing, same model, but now t is going to be 3.5 instead of 0.6. So let's evaluate that one. So 25 times e to the 1.386 times 3.5, and I'm going to hit enter. And then we're rounding to the nearest unit. Now in this case, notice our tenths place is 7. It's greater than 5, which means we're going to take the digit we want to round to and we're going to round it up. So rather than 3196, we're going to round up to 3197. So 3197. So in about half an hour, we a little more than doubled After 3.5 hours, we went from 25 to over 3,000 to about 3,200. So it's not adding on a certain amount every time. We're multiplying by a certain amount every time. The population is multiplying. We're not adding on one every second, anything like that. We're multiplying the size of the population. So then this one's going to be mind-blowing. We went from 3.5 hours. How much do we have after 24 hours of it sitting there in the dish in the lab? What happens? So now T is going to be 24. We're going to substitute that in place of T instead of 0.6 or 3.5. So we have 25 times E to the 1.386 times 24. Now hit enter. What does that mean? Remember, this E is not the same thing as this E. This E means 10 to the 15th power. In other words, take this particular number and take your decimal place and move it 15 places to the right. Now, you'll notice there's fewer than 15 decimals here. So what happens when you get to the end? Well, once you get to the end, if you have to keep moving your decimal, you're going to put in zeros wherever you have to continue moving. So if you were to take this particular number, move your decimal 15 places to the right, and then add in your zeros, this is going to be the number you have all the way from 3,200 up to this. What is this number? Well, here's thousands, and then millions, and then billions, and then trillions. This is what we would call quadrillions. So once we get past trillions, we're into quadrillions. That's about 7 quadrillion bacteria after 24 hours. So we went from about 3,200 in 3.5. After a full day, this is where we are, a ridiculously large number. That is exponential growth. So when we use the term exponential growth, we mean something is growing fast. We mean it's growing based on multiplication, not based on addition. This is the effect of something like that. Numbers get really, really big, really, really fast. So it begs the question, what would happen after 2 days? That you can only imagine what would happen. If you're curious, you could put in 48 instead there, and that would give you a number for that particular one. So this is a situation where we might have growth. This is a model for growth. We can know just from looking at it that it's going to model growth because the number in front of T, because our growth rate is a positive number. It's getting bigger over time, and that's our indication that this population is growing. Now let's look at an example where something is decaying, where it's shrinking over time. This is actually a really common example that you'll see in scientific contexts. It's called carbon dating. So this is used to date organic material just based on how much of carbon is left in it after it dies. So carbon-14 is a radioactive element contained in all living tissue. While a plant or animal is alive, the amount of carbon-14 in the organism is constant. Once the organism dies, however, the carbon-14 decays according to the following equation. So this is going to be the model for this particular decay situation, this particular exponential model. How do we know it's decaying? Look at the number in front of your variable t. In this case, it's a negative number. If it's a negative number, that means decay. That means the population is shrinking as time increases. So A is our output. It represents the amount present after t years. And A sub 0, that's our starting amount. That's going to be the amount present at time t. Okay, so let's answer a couple of different questions based on our model here, our model for decay. If 500 milligrams of carbon-14 is present in a sample of bone at time of death, how many milligrams to 2 decimal places will be present in the sample at 15,000 years? So if it sits there for 15,000 years, how much carbon-14 is going to be left in this sample of bone? Okay, so let's substitute what we know into our model. We know we start with 500 milligrams. So at time of death, that's where we start. Throughout life, this number is constant. At death, We start to decay from there. So that means 500 is going to take the place of a sub 0, which is our initial amount. Okay, now we want to know how much is present in the sample after 15,000 years. In other words, we're letting t be 15,000. So I'm going to substitute 15,000 into this model in place of the variable t. Now after that, all we have to do is plug that into the calculator and simplify it down. So it's going to look the same as plugging in for the previous example. The only difference is now the number is shrinking because our growth rate is negative. So 500 times e raised to the negative 0.000. Watch your zeros. Make sure you don't leave one out. Make sure you don't put in too many. It's 0.3 zeros. 124. Okay, times 15,000. And then hit enter. There we go. Now this says just round to 2 decimal places. In other words, we're talking about milligrams. It doesn't have to be whole units. We can have a fraction of a milligram. So to 2 decimal places, we're rounding based on the 6. The 6 tells us to round the 3 up to a 4. So 77.84 milligrams. So after 15,000 years, we went from 500 milligrams to about 78 milligrams. So what's happening here in terms of how things are increasing? Well, we can think of multiplying repeatedly by a fraction, or you can think of it as dividing. The population is dividing over time. So when we multiply over time by something bigger than 1, that means growth over time. When we multiply by something less than 1, or we think of dividing the population over time, that's when the population is going to shrink over time. Okay, let's look at another component of this example. This is something you might see if you take a chemistry class. So the half-life, what we call the half-life of carbon-14, half-life is related to any radioactive element. The half-life of carbon-14 is the time at which the amount present in one half the amount at time t equals 0. So we want to use the graph of this decay function to estimate the half-life of carbon-14. In other words, how long is it going to take in order to have half the amount that we started with? Well, here's our model. Remember, a sub 0 is 500. That's what we started with. What does that mean in terms of half? Well, what would half of that population be? In other words, if we start with 500 milligrams and we've shrunk to half of that, how much do we have left? Well, that would be 500 divided in half, which is going to be 250 milligrams. So the question we want to answer is, how long would it take to go from 500 milligrams to 250 milligrams? How long would that take? And this particular graph is going to model how we grow, how we decay in this case. Now, why do we know it models this situation with 500? Where's the 500? There's 500, with 500 to start with. How can we see that from this graph? Well, I want you to notice where the graph starts. If you think of this as being where t equals 0 and then we increase, notice where we are when t equals 0. We're right at 500 milligrams. So if you're looking at a graph, you can see the initial amount by finding your y-intercept. The y-intercept represents the initial amount. From there, notice that we're decreasing. That's because this is a decay situation. We end up decreasing because the number multiplied by our variable is a negative number. So the y-axis, or in this case the a-axis, A for amount, represents how much is in the sample at a particular time, which is along our x-axis, otherwise known as our t-axis. So at 0 time, when we start, we have 500 milligrams. We want to know how long is it going to take to get to 250. So where is 250 milligrams here? Well, it's going to be right between 300 and 200. So right between 200 and 300, this is going to be where we're at. So that's our output. The question is, what does t have to be for that to be our output? Well, we want to match that particular location on our graph to whatever we have along the t-axis. And I just realized I have a typo here. I didn't read this axis correctly. So let's talk through it, and you make sure you adjust your notes based on this, and I'll adjust the notes also on my end. The t-axis goes from 0, where it starts, to 50,000. So what's the scale? What are we counting by? Well, we're counting by 10,000, 20,000, 30,000, 40,000, 50,000. So if we're looking at the t-axis, what we want to know is what's the value of t associated with an amount of 250, halfway between 300 and 200. So in other words, we want to know what's the value for t associated with this particular location on our graph. And notice it does say estimate. We don't have an exact value here. We're just estimating based on what we see from this graph. Well, if you look right there and follow it down, we're going from 0 to 10,000. We're a little bit more than halfway between 0 and 10,000. So a reasonable estimate might be around 6, but not 6. What is it? It's 6,000. We're counting by thousands. So I wrote 6 here. My bad. That's a typo. I'll fix that. We need to go from 0 to 10,000. And so a little bit more than halfway. We could ballpark that at maybe about 6,000. Another way we could do that a little bit more accurately is if we were to take this function, use t as our variable, or in this case x, type it into the graphing calculator, we can probably get a closer estimate of what t would have to be, what our input would have to be associated with an output of 250. So that's another option as well. So that's a couple applications where we'll use exponential growth and decay. Notice they both involved this base e. E pops up a lot. E again was labeled as a universal constant because it just pops up in a lot of different situations. So these examples are not necessarily contrived examples. These are examples, particularly this one, that are based on actual real world numbers. So exponential functions, very, very relevant to real life. We're going to revisit these later when we look at financial math.